Welcome to Singapore Energy Center webinar. I'm Xu from NTU, and I'm the co-director of SGEC. This webinar is in fact the first one in the series. So we are very happy that all of you can join us this morning. And this morning, we are very honored to have Professor Siew to share with us his perspectives in sustainable energy future. Professor Chan is from School of Mechanical and Aerospace Engineering, NTU. He is President's Chair in Energy, Co-Director of Energy Research Institute at NTU in short ERAM, and Senior Vice President, China-Singapore International Joint Research Institute, which is in Guangzhou Knowledge City, China. Professor Chan has received many awards and recognitions, such as Outstanding Scientific Achievement Award from the International Association of Hydrogen Energy, USA, World's Most Influential Scientific Minds Award from Thomson Reuters, Star Innovation Talent Award from Guangzhou Government. Without further ado, let's welcome Prof. Chan to deliver his talk.
Thanks, Prof. Xu, for your kind introduction. Now I'd like to share my screen. Well, this seminar is on hydrogen and fuel cell technology, a bridge towards a more sustainable future. Well, it's a combination of a more general kind of knowledge as well as a more technical. It's a combination of the two. So I would like to first share with you the renewable energy, because anything that decouples from a renewable energy is meaningless. I would like to share with you the number, right? So if you look at the energy absorbed by the Earth atmosphere, that is the air, ocean, the water, and the land masses, is 3.85 exajoule every year. If you divide this number with 365 days, you will get more than 10,000 exajoules in a day. Photosynthesis, on the other hand, would absorb 3,000 exajoules of the energy per year. So this is solely for the solar energy. Of course, there's a wind energy, there's a geothermal, there's many other types of renewable energy. Just the solar energy alone, you can see that, every year, we absorb 3.85 million exajoules of the energy. And you would like to know that what is exajoule? Exajoule is actually 10 to the power 18 joule, or equal to about 22.7 million tons of petrol equivalents. Now let's look at the world electricity consumption. In year 2018, it is only 84 exajoule. This is for the whole year. And every day, this is a daily kind of energy that we absorb. It's far more than this. And if you look at the primary energy consumption, in 2019, it is slightly more than 500 exajoule in a year. But in the day, we have all this energy, right? So 1 year of the sunlight is twice as much energy as will ever be obtained from all non-renewable sources on Earth, including the coal, oil and gas, and the uranium. Imagine that 1 year is sufficient for us, not sufficient, it's twice the amount of non-renewable sources. Since we have all this, a lot of energy, then what are the issues? The issue, just capture a few. The most serious one is a spatial and a temporal distribution of the energy. This one is geographical. Certain country has oil, certain country do not have oil, right? Certain country has, strong wind, solar energy, but certain country, has nothing. For example, Singapore, we have a little solar energy. Other than that, we don't have any other good source of the renewable energy. Temporal distribution is like, function of time. Like for example, solar energy, we have daytime, we have the solar energy. The nighttime, we do not have. So this is a time in the time domain different. So in other words, we are unable to match the supply to the demand, right? And of course, lacking of a proper storage, kind of energy storage kind of solution. Apart from this, there are many other things like financing. Certain poor country is unable to have a power plant, even they have oil. So we need to financing issue, and also some political kind of issue. There are many others. I like to share this, thermodynamics applied to a multi-energy system, right? So this is the only equation that I use, right? So this is actually, energy balance applied to a control volume, right? In the thermodynamics terms, all energy on Earth can be classified solely into three types: the heat, the work, and the mass. Typically, if you look at the heats, you all know that we have a conduction, convection, and radiation, and this lead to the heating and the cooling. Work can be mechanical work, but here we would like to focus on the electrical work, which is the electricity. Mass is easily understood. Coal, oil, and gas, these are the mass, right? So if we look at a township, right, a city, a town, if we draw a boundary around their township, right, so the township is a system. It interacts with the surrounding in terms of these three types of the energy: heat transfer, work transfer, and the mass transfer, right, which is the left-hand side of the equation. So these are the so-called the parameters across the system boundary, whereas the right-hand side is the change of the properties within the control volume itself, right? So if we now look at the situation that if we scale up, the township becomes a biggest town. So this would mean that we amplify the issue of the supply and the demand, right? When the supply meets the demand, the storage will have a zero, meaning that the change of the storage remain unchanged. If the supply is more than the demand, the storage will increase, or the other way that the demand is becomes more, the supply is less, then we will have a depletion of the storage. So this would lead to different types of the storage required: the gas storage, the charge storage, and the thermal storage, right? So is this a case that we should increase the storage if we scale up the township? So this is not desirable. So what we wanted to do is to convert the energy from one form to the others, right? So these are the energy that can convert from one to the others. A typical example is the cogen plant, right? Cogen plants start from the mass using the gas, right? We can convert the gas, the mass, into the electricity in the form of power generation. We can also generate the heat, so this is the concept of the cogen. You can play with the ratio of the electricity and the heat from the cogen plant. So we have to, link this up so that we can convert one form to the others, not necessary to increase the size of each storage. Now let's look at how this can be done, in an ideal world. So if we have a hydrogen or any hydrocarbon fuel, we can, oxidize the fuel in the fuel cell electrochemically, generate the electricity, and the byproducts can be CO2 and the H2O, right? Now we link to the so-called the renewable energy. If we use the renewable energy to electrolyze the waters and the CO2, we can produce a syngas. Syngas itself is an energy, and it is also an energy storage, right? If you think that you want to convert the syngas to the hydrocarbon fuel, again, this can be done through the Fischer-Tropsch process, right? So these are all established kind of a technology, right? So you can convert like this. So in this talk, I will focus, in the later part, will focus on the co-electrolysis of the CO2 and the H2O, right? Which is the result of the oxidations of the hydrocarbon fuel. And you have this CO2 and the H2O as the exhaust, as the emission in the exhaust. This is a busy slide, and like to share with you the evolutions of the energy use, right? Let's look at the right-hand side of this diagram. The x-axis is the year, the y-axis is the ratio of the hydrogen to carbon, right? So this is the HC ratio. We started the plot from 1800 and then end with 2100, which is the end of this century. We started from here because hydrogen was discovered in 1766, and then the name was coined in 1783, around this time, right? So then let's look at the red dot. So this is post-industrial revolution where the demand of the energy is increased. So you can see that earlier on, we actually used wood as an energy to supply the energy that we need. Then when we move to hydrocarbons and then the oil, and finally the methane gas. Today we use more methane more than ever, right? So when you move along the times, the years, you can see that the HC ratio is actually increased from 0.1 to currently 4. And in future, we will expect that, you know, we will use the hydrogen when we move towards the renewable energy era. So this is the evolution of the energy use, right? We know that the carbon in the field is reducing, you know, relative to the hydrogen. So, and ultimately we were 100% kind of a hydrogen that is serving as our energy carrier. On the left-hand side of this slide, you can see the energy density, right? The x-axis is the gravimetric energy density. The volumetric energy density is on the y-axis. Hydrogen has a very high gravimetric energy density, but the volumetric energy density is low, right? But luckily, hydrogen can be compressed to increase its volumetric energy density. And liquid hydrogen is actually about 10 megajoules per liter, right? So this is the highest among different types of energy in gravimetric energy density sense. So ideally, we are able to find, you know, types of the energy or energy carrier that has high gravimetrics and the volumetric energy density. So let's look at the demand. Energy density, and particularly important for those of the grid application. A car, you know, required 2 gigajoules of the energy. A bus increased in order to become 20 gigajoules. A380s, 11 terajoules. Space shuttle, 27 terajoules. And the big cruise ship is about 300 terajoules. Right. Now let's look at what energy that we have, right? Hydrogen, just now I mentioned that we can compress it at a different pressure. Gravimetric energy density, this is based on the higher heating values, is a very high. It's not an issue. The issue is with the volumetric energy density, right? And look at the liquid ammonia, right? The gravimetric energy density is not too bad, 22.5, right? Megajoules per kilogram. And the volumetric energy density is actually higher than the liquid hydrogen. So that is why there's a lot of interest on liquid ammonias for the ship propulsion, right? Syngas itself, if you compress at the 30 bar, it has a very high gravimetric energy density, but, you know, low volumetric energy density. Lithium-ion battery, if you look at both gravimetric and volumetric energy density, they are low. So we can see that, you know, batteries perhaps can be used in a car, at most to a bus. You know, when we move to other types of a propulsion system, you know, we should rule out the battery for the time being. And this is something that always people ask me that, hey, battery is useful or fuel cell is useful? So today, I'd like to address this question by telling you that what is the power-intensive application and what is energy-intensive application, right? The y-axis is in terms of times, right? From 2 to 7 hours onward, we call it energy intensive application, below which we call it power intensive application. And the x-axis is the power. So if you look at the battery covers, from a small to big powers in terms of a power intensive application, right? We are talking about 2 to 7 hours kind of range. When you talk about, higher than 7 hours, when we're talking about days, weeks, even season, we have to look at different options, right? The most successful one for high power and longer times kind of application is the pump hydro, as well as compressed air energy storage system. And hydrogen and oxygen storage system can actually cover this part, right? From a low power and to high powers, from 2 to 7 hours onward, we can actually consider this, right? So this is, the highlights of today's. Excuse me, I think I need the light. I stopped moving and the light is off. So let's look at this this courtesy from EPS Singapore. So I get this slide from them. So this is the hydrogen energy storage system, right? And it can store 16 megawatt at a low pressure of 30 bar, and the size is about 1,000 square meters. For the same energy storage, but when we increase the hydrogen and the oxygen's pressure to 150 bar or 5 times, the size can reduce to half, 500 square meters. So this still look big, right? But let's look at the next slide. Look at the size comparison, right? So this is a solar farm, right? The solar farm would have 10 megawatts of solar PV, right? And then 16 megawatt hours of energy storage, right? Now, if we use the hydrogen and oxygen as an energy storage, right? Under high pressure, the size is only 0.3%, of the solar farm. If we reduce the pressure to 30 bar, and then this is 0.6%, slightly increased, double the size, but still small enough compared to the solar farm. So how big is this solar farm? In order to provide, in order to allow a 10 megawatt solar PV installation and 16 megawatt energy storage. So this is 400 by 400 or 22.4 times of the soccer field, right? So this gives you the dimension, the comparison. Next, let's move on to different types of hydrogen production technology. This is fossil fuel based. I think you all are familiar with steam methane reformings, as well as coal gasification. So we have different types. We have steam methane reformings, and we have partial oxidation. We have autothermal, right? So you can see that the efficiency are different from different types of thermochemicals kind of a conversion. And let's look at a large one, right? Steam methane reformings, and with a CCS, the efficiency based on the lower heating values is 61 to 70%, right? And if we do not consider the compression, then this will have a highest kind of efficiency, right? 62 to 78%, for a large scale steam methane reforming plant. And for the coal gasification, with a CCS and cogen using membrane separation, it can reach 77%, right? So there are different types, current gasification, the future, if you use the oxygen together with the carbon and the waters, and then, you would have a better kind of efficiency relative to the current gasification. The next will be by electrolysis, right? Hydrogen production based on the electrolysis. We have a different technology. This is a more mature one, alkaline, large scale alkaline, high pressure, advanced alkalines, PEM, and solid oxide electrolysis cell. So this data were pulled from IES, and PEM now is actually under commercialization, right? Their operating temperature, the amount of the energy, electricity required per kilogram of hydrogen produced, right? And the efficiency based on the lower heating values. Compared with alkaline electrolysis cells and PEM, solid oxide electrolysis cell has actually the best efficiency from 85.5%, which is higher than the PEM, to more than 100%, right? So you may question that, why the efficiency can be more than 100%. So I have to highlight that this is the electrolysis to enthalpy of hydrogen conversion efficiency. And I will tell you why, the efficiency can be very high. Another types of hydrogen production technology is the catalytic decompositions of methane. And because this is neither blue nor green, so a new term is called turquoise hydrogen, because when hydrogen is extracted from a methane, it will not produce any CO2. Instead, the solid carbon is produced, right? So we propose using the rotary reactors, feeding the gas, and then under the pyrolysis, we will generate the hydrogens and the carbon. So I do not want to go into the details, but this is the new ways and other methods for hydrogen productions without CO2 generation. So this slide gives a summary that, a different pathway, hydrogen pathway. It can be a thermolysis using the heat, electrolysis using the electrons, photolysis using the photon, and hydrolysis, like for example, the chemical hydride, react with the waters and generate the hydrogen. So why high temperature electrolysis? Today's focus will be very much on the high temperature electrolysis, right? So this will also explain why the conversion efficiency in electrolysis, just like I mentioned, can be more than 100%. If you look at the heat engine, we know that we provide the fuel, which is the source of the heat, and generate the mechanical work in a car engine, and you have a heat sink that discharges to the atmosphere. The efficiency is smaller than 1. And the fuel cell is actually working similar to the heat engine, right? You draw in the fuel, produce the electrical work, and then you have a heat sink, so the efficiency is less than 1. But electrolysis is actually working similar to a heat pump, right? Instead of putting in the fuel source, we put in the electrical work, right? And then the heat is actually mobilized from the source to the sink. So the COP, instead of efficiency, we use a term called COP, coefficients of performance, can be greater than 1. It can be 3, can be 4, right? In a so-called the heat pumps context. Electrolyzer work similar as the principle of the heat pump. We put in the electrical work and we can mobilize the heat from the surrounding. So the combination, the work, which is our input, plus the heat from the surrounding is actually equal to the energy sink. So that's the reason why that the efficiency can be more than 100%, right? And interestingly, if you look at the temperature, when we operate at a high temperature, the electrical work demand is actually reduced and the heat from the surrounding is increased. So, and this is the output. And when the temperature increases, the gap is become bigger. So the efficiency, from electricals to enthalpy is actually increased, right? When the temperature is increased. So this explains why we wanted to operate at a high temperature. But of course, the electricity ideally coming from the renewable energy, right? Either using the wind or using the solar energy. Okay, electrolysis is not just simply applied to water, right? And most of the time, you are familiarized with water electrolysis. right, we can actually apply to the CO2 as well. You know, the first CO2 electrolysis was actually one conducted for the space mission, right? Because on Mars, planet Mars, the atmosphere is mainly CO2 and carbon monoxide, right? And the astronauts required the oxygen. So you can actually electrolyze the CO2 to produce the oxygen for breathing. So we can actually, using the waters, electrolyze the waters to produce the hydrogens, or electrolyze the CO2 to produce the carbon monoxide. Of course, we can co-electrolyze the two to produce hydrogen and carbon monoxide, which is the syngas, right? So let's look at now the flue gas electrolysis, right? The flue gas especially from an oxy-combustion plant. The flue gas are nothing more than CO2, waters, oxygen, salts from the field without nitrogen, because it's from an oxy-combustion plant. And once it is electrolyzed, you will produce a syngas, and the salts will become hydrogen sulfide, which can be removed later, right? So electrolysis can also apply to air. We can actually separate the nitrogen from the oxygens by using the electrolysis, and this serves as an air separation, right? And the wet air electrolysis, wet air containing air, which is consists of nitrogen and oxygen plus the water because of wet, right? When we electrolyze it, it becomes the feedstock for ammonia, right? And all this method, the byproduct is actually the oxygen, right? Now, this is a typical case to produce a syngas. I have one animation, right? Going to the electrolysis, the flue gas containing CO2 and H2O will ultimately become a synthetic gas, and the byproduct is oxygen, right? So this is a single step, right? By injecting the electrons, and you separate, you generate the syngas. So this is a typical oxy-combustion plant, right? Essentially, you have a two system. One is the power plant, oxy-combustion power plant, and the other one is solid oxide electrolysis cell. So the flue gas from the oxy-combustion plant contain rich CO2 and CO2, and also the waste heat, right? Once this is, the gas is electrolyzed, it will produce the syngas, and we can use the excess energy from the power plant or from the renewable energy. So essentially, we bridge the fossil energy to the renewable energy, right? So this is using the fossil energy, and this is the renewable energy. We bridge the two, right, in an energy transitions era. And interestingly, the oxygen, which is the byproduct from the electrolysis cell, can be channeled back to the power plant, right? You know that the power plant required a lot of oxygen, then this oxygen can be used in the power plant. And the so-called syngas produced as a result of electrolysis can further convert to synthetic fuel, through a Fischer-Tropsch kind of a process. Right? Now let's look at this, look at the number. Right, you have a power plant and you have an electrolyzer. Assuming we burn the methane gas, we required 2 moles of the oxygen to generate 1 moles of a CO2 and 2 moles of waters. And once we use the renewable energy to electrolyze it, right, we produce 1 mole of a CO and 2 moles of a hydrogen as a syngas. And the byproduct is a 1.5 moles of oxygen. We can feed it back to the power plant. So look, we require 2 moles and we are short of a 0.5 mole. 0.5 moles of oxygen can be obtained from the air through the dry air electrolysis. Just now I showed, again, you use the renewable energy to do so. And we can form this closed loop, right? And look at the heating values of the syngas per unit mass of the methane burn. Right, methanes produce 1 moles of a CO, 2 moles of hydrogen, right? So 16 kilogram of methane produce 28 kilogram of CO and 4 kilogram of hydrogen, right? And we make it to a per kilogram basis. And then this is the heating values of methane, carbon monoxide, and hydrogen, right? By considering the heating values, meaning that 50 megajoules of methane, which is 1 kilogram of methane, produce 47.5 megajoules of syngas. And this energy is actually taken from the renewable energy, right? So we form a closed loop, carbon neutral, right? The carbon is actually reused and route back to the power plant. So now I'd like to show you some more technical stuff. This is a test facility that we have. We are using a cell. The electrolyte is yttria stabilizer cornea, and this is the anode, and this is the cathode LSCF, right? And this is forming a stack, and this is a test station, and this is the cell mounted on inside the furnace. So let's look at the electrolysis, right? The SOC or solid oxide cell is the only technology that can run on fuel cell mode and electrolysis mode reversibly. You know, you can run on fuel cell or electrolysis using a single device. Unlike other technology, right? Like PEM fuel cell and PEM electrolysis cells are totally different devices, right? But solid oxide cell, you would allow you to run on the different mode. And it can produce either the electricity, you know, when you operate in a fuel cell mode, or hydrogen when you operate in a electrolysis mode. And the hydrogen can serve as an energy storage, right? So you can see that we are actually running from electrolysis mode to the fuel cell mode. You can see that the curve is very smooth. And at this line, zero current density, this is the open circuit voltage, right? When you operate the cell, either in the fuel cell mode or electrolysis mode, if you are close to the open circuit voltage, the efficiency is the highest, right? Now, in this case, we are running at 3 different atmosphere. The green color one is 3% of waters. Water is actually the feedstock for the electrolysis, whereas the hydrogen is the feedstock to the fuel cell, right? So you can see that the green color is favorable to the hydrogen fuel cell, but it's no good for the electrolysis because the concentration is very low. So that's why you can see, you know, the running at this condition, we reach the limiting current at a very low kind of a voltage, right? And when we increase the water content, you can see that the performance improves, right? We also run the impedance test to show the impedance variation, right? Essentially, the ohmic resistance will not change very much. It's rather constant, but the polarization resistance will vary with a different kind of a DC bias. So let's look at the this slide, you know, showing that different atmosphere again. And I would like to share with you that, you know, looking at the 2 important parameters. One is the current density at 1 amp per square centimeter. Current density, the highest, meaning that the highest the yield, right? So what we want is to achieve a reasonably good kind of a current density, you know, at low voltage. Just like I mentioned that the lower the voltage, the higher the efficiency will be, right? Another criteria is look at, you know, if you compromise with the efficiency, you know, say at 1.4 volt, what will be the so-called the yield, you know, the current density, which is related to the hydrogen production rate. We all know that 1 amp is equivalent to 7.6 cc per minute of the hydrogen generation. And we can easily calculate, you know, from the current to generate the hydrogen production rate, right? From the current divided by 2F, you will get the molar ratio multiplied by the heating values divided by the power, right? Divided by the power, then you can get the efficiency. CO2 electrolysis, right? Similar trends in the DC polarization, right? As the water electrolysis. The electrolysis current increased with the CO2 concentration because this is the so-called the feedstock, right? And the higher the temperature, the higher the current density will be. So higher temperature will be favorable to the yield, right, from CO2 to generate the carbon monoxide. So a typical limiting current density behavior was observed at a high voltage. Right? At a high voltage, you can see that especially the lower concentration of the feedstock will reach the limiting current. Right. Now let's compare the waters and the CO2 coming to an end. Bear with me. So we have different types, right? Various electrolysis behavior, i.e. water electrolysis, CO2 electrolysis, and co-electrolysis, which is the case of CO2 and hydrogen, because the CO2 and hydrogen will first go through the water gas shift reactions and to generate the waters and with the remaining CO2, and then the electrolysis is simply the case of the co-electrolysis, right? Much higher current density was observed for the water's electrolysis than the CO2. You can see that, right? Than the CO2. So this actually tells you that water is easier to be electrolyzed compared to the CO2. And this is the co-electrolysis, right? Remember just now we mentioned that if we, in an oxy-combustion power plant using the methane, right, we will produce 1 moles of a CO2 and 2 moles of waters in the flue gas, right? Now we have 3 cases. The co-electrolysis performance of the cell was slightly improved with increasing the water CO2 ratio, right? From 1 to 2 to 1 to 2, 1 to 1 and 2 to 1. 2 to 1 is actually this case, right? 2 moles of waters against 1 moles of the CO2, right? And you can see that they are actually more or less the same. This diagram actually shows you that co-electrolysis is possible, and it is not very sensitive to the ratio of the waters to a CO2. You can see from the polarization curve, they are more or less the same, And if you look at the OCV as well as at 1.4 volt, the current generated are more or less the same, right? So co-electrolysis using the SOEC is possible. Now I'd like to conclude. Energy storage is an essential component in any energy system due to the mismatch of the supply and the demand. And energy storage issue is amplified with increasing penetration of renewable energy, especially those with an intermittency nature. That's why you have to store it. Converting one form of energy to another form of energy based on the need would reduce the physical size of each principal storage. So that's why we introduced the co-electrolysis of the flue gas, right? So we wanted to convert from one form to the other form. Hydrogen and the fuel cell and electrolyzer can facilitate the energy conversion among heat, work, and the mass in thermodynamics term. Converting waters and CO2 to syngas in a single step is possible by high temperature electrolysis. Thank you.
Thank you, Prof. Chan, for giving us the wonderful talk. Okay. Thanks, Prof. Chan, for giving us a wonderful talk, which has given us a big picture about the energy system, as well as some knowledge about how hydrogen and the fuel cell technologies can bridge the gap towards a sustainable future. So right now we have Q&A session. The participants, you can type your questions in the Q&A, the chat box, and I will read out the questions for you. So while we are waiting for the questions from the participants, I can start maybe asking 1 or 2 questions. So Prof. Chan, could you share with us what are the major challenges in this SOEC technology right now? What we need to solve?
It's still the cost. Unlike PEM, the production cost is low. I'm not sure whether you still remember that in 2005, Temasek, together with our other company and Rolls-Royce, set up a consortium called Analtech, and we put in $100 million, aim to develop a 1 megawatt solid oxide fuel cell system. Well, SOEC and SOFC are not much different. As just I mentioned that you can, reverse the operation. But of course, electrolysis had more issue than the SOFC. But everything is around the cost. Making solid oxide fuel cell is very challenging. If you look at from the performance perspective, you hope to be able to achieve a very thin kind of an electrolyte layer, for example, 10 to 15 micron, and pinhole-less, meaning that it's 100% dense. Imagine that if you wanted to sinter any ceramics and to achieve close to theoretical density, it is not easy. So that is the challenging there. And again, when you scale up the so-called the size of the so-called cell, warpings, deformation can easily occur. So it's not easy to make a whole piece very robust. The integrity is good, and it's very challenging. And I remember vividly that the rejection rate is super high, meaning that when you make maybe 1,000 pieces, more than 500 is rejected. So that is the challenge of the so-called from the production. Making it in the lab is always easy, right? When you do the so-called the mass production, looking into the cost factors, and this is always difficult. And in the case of the solid oxide electrolysis cell, look, just now I show you that the anode is actually using the nickel. Nickel can be oxidized by water and CO2, especially when prolongs operation at an idling condition, meaning that at open circuit voltage, because at open circuit voltage, hydrogen is not produced. Then the waters, the oxygen in the water can oxidize the nickel at high temperature. So nickel to become nickel oxide causing chemical expansion, then the electrode will be failed. So to play safe, you can actually, you still can use the nickel by mixing the so-called the water with certain percentage of hydrogen to create the so-called reducing environment for the anode.
Thank you. So we do have questions right now. Let me read some of those. First question is from Jia Ying Si. He or she asks, which is the most suitable off-the-grid application for SOEC? Off-the-grid application.
Well, off-the-grid, normally we are talking about two broad categories. One is for the propulsion system, for the car, for the aircraft, for the ship propulsion. Anything that related to propulsion system required a fast response. Solid oxide electrolysis cell is not a fast response devices. It can only be used for the so-called stationary power, right? So to answer the question in short, solid oxide electrolysis cell can be applied to the stationary power, but not the mobile. These are all off-the-grid applications.
Okay, thanks. One question, which is on a kind of different aspect, is from Junpo, or Junpo, who asked about, apart from power generation, how about the hydrogen safety issue for PEMFC? Can Prof. Chan share your thought?
Well, safety is always a concern. I won't say that hydrogen is safe, and we should say that other form of the fossil energy is not safe too. We need a proper kind of a handling procedure, not just hydrogen, including hydrogen carriers such as ammonia, right? So the safety part is always a concern, a lot of a discussion around this, and we need to come up with a so-called code and the standard and the practice, when we handle the hydrogen? So this is my simple question. It can never be safe, when it comes to the explosion, right? Leaking is not too bad because hydrogen is light and you can disperse very fast, but if you trap in a so-called closed kind of environment, and because of the wide range of the flammability, you can easily trigger the explosion.
Thank you. We do have a specific question about what should we pay attention to when we switch between the fuel cell and electrolyzer?
Most important thing is the temperature, right? So when you switch from the fuel cell mode to the electrolysis mode, the water is coming from outside. The water has to preheat close to the so-called operating temperature. If not, the water will quench, the cell, causing cracking problems. So this is something that have to be very careful. And just like I mentioned that, either solid oxide fuel cell or electrolysis cell is not suitable for those fast response kind of application, right? Even for the fuel cell, imagine that during the winter, your gas coming in maybe at, close to ice point, 0 degrees C. You have to heat it up, the gas, heat it up to temperatures normally is less than 100 degrees C, different between the operating temperature and the fixed stop temperature. Then you will ensure that, the operation will be smooth. If not, is that this will cause the damage.
Thank you. There are several common questions about what's the maximum capacity for SOEC.
Well, you can see that basically it can be very compact. I don't think that currently there's any technology can produce hydrogen, the quantities close to the electrolysis, except the traditional, which steam methane reformings, we are talking about emerging technology involving no CO2, right? So if you look at the power density or the current density, imagine that 1 square centimeter, you can produce 7.6 cc and at the efficiency close to 100%, right? And imagine that if you have a 10 by 10 centimeter and many cells, you can actually generate tremendous amount of the hydrogen, right?
Okay, so one general question, could you share your view on alkaline electrolyzer membrane technology versus PEM versus SOEC?
Well, we should not rule out the alkaline membrane. Unlike in the past, we are using the liquid electrolytes. Now, people are moving towards the so-called solid state kind of membrane. The costs remain low, competitive. So it is actually very challenging. We do the cost analysis. Hardly can beat the cost of the alkalines in terms of lifespan, as well as the compromised kind of efficiency cost. So yes, I think that I still think that alkalines electrolysis cells still have a room to play. And most importantly is that unlike the PEM, in the alkaline environment, you can use non-precious metals catalysts to achieve the electrolysis. So this is the plus point for alkaline electrolysis cell.
We do have a few minutes for a few more questions. How about the stability of this system?
Of what? Of
SOEC, yes.
Oh, if you look at the DOE kind of target, the lifespan, including the stabilities, is much longer than the PEM. We are talking about 100,000s of hours and above. So in terms of the durability, solid oxide fuel cell is much longer. But of course, it is not suitable for start-stop. When you operate it, you know, 24/7, days, months, continuously. You don't start and stop. If you start and stop frequently, it can cause failures easily.
Thank you. One question from Nelson Low is, Boeing is betting on hydrogen-powered aircraft. How far do you think we are away from this goal? Other than cost and infrastructure, what are other challenges?
Yes, I heard about this. I think, that hydrogen fuel cell has been applied successfully for the UAV, right, which is a small aircraft. Moving to the big one, initially it can be a stationary, it can be the so-called the power source for the aircraft. It is still far from use as for the propulsion. You can use as a source of the powers, but not for the propulsion, right? So that is the reason why that we still have to look at the hydrocarbon fuel. Ideally, is that that is from the synthetics, from a CO2 and hydrogen. We convert it back to the kerosene. If you wanted to decarbonize the aircraft, that is probably the most challenging, including the ship propulsion as well, because they are high power devices. They consume a lot of fuel. They require a very high energy density. So these are all the issues. It's still a distance, I would say that this perhaps is the last to kick off.
Thank you. One question is about, from SOEC, can you directly produce methane so that we don't have the hydrogen storage issue?
Well, you can, just like I mentioned that, you can co-electrolyze the syngas, and then after that, you can, through a Fischer-Tropsch process to produce a hydrocarbon fuel. You can, of course, couple the two together in order to prevent the so-called any losses, right? So you can couple together, but I don't think that you can do it in a single step, putting in the so-called the flue gas and generate the so-called hydrocarbon fuel. I don't think so. I don't think that this is possible at the moment. There are some research doing something that, in the exhaust with a certain catalyst and that you have to pressurize it, that is not something that is easy.
Okay, I guess maybe we will take two more questions. One question from Shaw Ito is, currently one of the industrial customer wants to establish fuel cell system for construction machines. Do you consider it makes sense in energy point of view?
Well, it's always possible, especially when human is replaced by robot, and then you really need the so-called powers for those robot. I mean, the robot can carry out the construction work, right? Service robot or whatever kind of construction robot. And the power, of course, is essential. Ultimately, it boils down to the cost, and the infrastructure to support it. Even you have a fuel cell, can you easily obtain the hydrogen, right? Do you have a supply chain that, in place, to support this? I think that this will take a while. Everything is around, the infrastructure to support such application and the cost.
Okay, one last question. This is interesting. Whether hydrogen fuel cells can be used in gadgets in near future? What are the advantages and drawbacks?
Well, there are micro fuel cell. I think my colleagues, Professor Siew, is actually working on solid oxide base kind of a micro fuel cell. The micro is really micro, meaning that 1 square inch will have probably 500,000 cells, and the cell can interconnect together. And because of the cell is so thin, they had to build on the wafer, right? So you can look at this, for specific kind of application. But on the other hand, let's look at the so-called the gadget. The gadget required very small amount of the energy, right? And the storage, which is a battery. is more than sufficient to support the gadgets unless the gadget consume very high energy, or high power kind of devices. If not, they said fuel cell will not have a so-called competitive edge, compared to the battery, because fuel cell is an energy conversion device. In order to miniaturize it, that is a challenge. So fuel cell will only be competitive when we are looking at high powers, high energy kind of a consumption. Just like I showed a slide from a vehicle to a bus, then to the aircraft and the ship propulsion. If you're going to the right-hand side, which is the high power consumption kind of a devices, high energy consumption kind of a devices, then fuel cell will make more sense for this application. If not, let's say you compete with a battery, you may not have any competitive advantage.
Thank you. I guess we need to answer one more question. This was missed earlier on from Chi Xiang Lim. Prof. Chan, for flue gas from oxy-combustion plants, is it applicable for Singapore where the concentration of the flue gas is low from combustion of LNG? It seems the flue gas is only for high concentration CO2 in coal power plants.
Well, oxy-combustion plants has high flue gas in terms of CO2 and H2O. Oxy, because that if you look at a carbon gas turbine power plant, about 5% of the CO2 in the flue gas. This is because of the concentration of CO2 is diluted by the nitrogen, which appear in the air. And air, assuming that is inert, right? So whatever you take in nitrogens from the air, you will discharge the nitrogen, and only very small amount become NOx, right? So for this reason, that if you apply it to the so-called normal combustion power plant, the CO2 concentration, the percentage is very low, which is not applicable. Just now what I mentioned is for oxy combustion power plant, for example, in the steel industry, glass industry, because this industry require high temperature heat. So you burn with the oxygen instead of the nitrogen, because when you're using the air, contain a lot of the nitrogen, it can dampen the temperature, can dilute the temperature. So that's why oxygen is used in the steel industry, as well as in the glass industry, steel smelting industry. So as long as the oxygen, the air, the oxygen contain no nitrogen, then it can ensure that the exhaust gas has a high concentration of the CO2 and the H2O.
Thank you. Thank you, everyone. Thanks, Prof. Chan, for answering all these questions. We may have missed some of the questions in the chat box due to the time constraint. For your information, the whole talk is recorded, will be posted on SGC website. So feel free to watch the video later or send the link to your other contacts. So we have come to the end of this presentation. Thank you for your participation. Please look out for our future webinar announcement. Thank you. See you next time and stay safe. Prof. Chan, please stay here.